to AI, software systems, and manufacturing. Let's join me in welcome Professor Sriram.
Thank you very much. Okay, that was a little bit past in the president of Washington Academy of Sciences. So my term is over. So that means that must be at least 2 years old. Anyway, again, thank you. My name is Ram, and I'm Chief of Software and Systems Division. I guess you addressed me as professor. I guess once a professor is always a professor. It doesn't matter. I'm no longer a professor. So this talk is going to focus a little bit on manufacturing. Also, I'm going to talk a little bit about AI from my perspective. There's a lot of perspectives of AI floating around. So some of this may be repetitive to some of you, but bear with me on that. Okay, I can skip a lot of these things if you want to. And also the slides will be available. I'll send it to you. So if people want the slides, you can distribute to them. And you're recording, I guess, so it's all probably available for people who want to watch it later on at their own convenience. So let's start with, again, I'm focusing on manufacturing. My two areas are manufacturing and healthcare, and I can talk on either of these subjects with the same level of non-expertise or expertise, however you look at it. So in terms of the manufacturing trends, as you know that we kind of started, how many of you are actually in mechanical engineering here? Okay. Yeah, that's good. That's good. At least 3 of the rest of our AI people looking to work in manufacturing. Because I don't know why this topic was chosen, but anyway, since we're good then. And even if you're not in manufacturing, you'll get into manufacturing after this talk, I hope. So if you look at it in the olden days, in the early 20th century, we started with this mass production kind of thing. And I guess you all know Henry Ford, who said that you produce any cars at any amount as long as it's black in color or something like that. So that's a famous saying. So from that around in the 1950s, at about 70s or so, we got into this, customer-driven manufacturing. And because of the advent of this ICT technologies, that is the information communication technologies. So we saw a lot of computers entering into the manufacturing world in various places like inventory management and so on and so forth. And then what happened, and then there's some AI work also went on in there, but not so much, but it's mostly CAD-centric kind of work. And then there's a lot of stuff on manufacturing floors, manufacturing simulation, and those kinds of things in terms of from a computational perspective. Again, my field is what is known as a computational thinking. So I look at how can you use, it's basically application of computers in various fields, and manufacturing is one of the fields that I've been working on. So then then we started into this 21st century manufacturing with the advent of internet. Okay, that's the key thing. Internet started, I remember I was at MIT about 40 years ago, and at that time, people thought internet was for email. I don't know how many of you used internet 40 years ago, AOL.com and those kinds of things. They seriously believe internet could not be used for anything else except the internet. So we had some trouble with that. So in terms of this network-centric manufacturing, you see there's a lot of networks around here. There's a design network, there's a production network, there's a distribution network, and all kinds of networks there. What I'm going to do is to show you an example of one such network, the design network, and other networks have kind of similar characteristics as such. Interestingly, though, this particular design network, this work I did at MIT, and then when I came to NIST, I did the slides in 1996. This is a slide of 1996. Okay, and things have not changed that much. Let's see why they have not. And the idea there was that going from customer specifications, because that's the first part, and then using something called house of quality and so on, you map that into engineering specifications. Because being engineers, we are really interested in engineering specifications. Because someone may say the car door should close, because that doesn't help you. You've got to say what's the kind of force in there, what is the tolerance gaps, and all kinds of things from an engineering perspective as such. Okay, and a lot of times what happens is that people actually, even software is the same problem too. For those of you who are working in software, software specifications are important, and you have to be very unambiguous about software specifications. And in fact, I was in India once, and then they had this fantastic building, modern building, except there's water all over the place. So when I asked them why there's water around the place, they said, well, see, the specifications did not say it has to be waterproof. So when it rained, because apparently in this place it doesn't rain that much, so that was a problem. So this is important. And in the specifications, for example, if you're in the software world, it's very important that you do it in a formal way. Anyone here doing software engineering? So it's the software specifications have to be in a formal manner. That's where logic comes into picture, and you all know. So you kind of put this in some kind of a design network, and now actually it's all cloud. If I have to change this slide a little bit, all of them will be in the cloud. So everyone puts this. This was in 1996, so we are putting it on this design network. So then you go to this, all the information you put in goes into this database. Now, one of the important things here is that people don't realize very much is databases actually play a big role in these kinds of things. And nowadays, what is happening is that you have a whole lot of natural language processing going on. I'm not going to talk about NLP work that we are doing, because you take this engineering specs and engineering standards and using natural language processing. Tim is very familiar with that. Using natural language processing, you actually extract the terminologies and the relationships between these various terminologies. So that plays a big role. And we are doing considerable work in that area, such which I won't touch upon in this lecture, but if anyone is interested. So then you kind of convert this into some kind of a database format. I call it the design evolution database, but there's all kinds of things involved in. So let me see. And I wonder what happened here. Okay, anyway, sorry about that, some repeatability here, but in any case, let me just go through the process here. It's a workflow here. And actually what happens is, once you have the specifications, the first thing you have to do is come up with some kind of a conceptual design. I have some engineering specifications. I want to know how these things kind of look like. So, so the first step there is this knowledge-based design kind of thing. This is the good old days of 1980s, where it should probably sit down here, okay? And this particular thing, let me see. This is a guy named Alan Mulally. He was the Boeing chief engineer, and this is for Boeing 777. And he made this statement in 1992. Listen carefully what he made, okay?
Now, computers don't design it. We don't have, we have not put the knowledge that's in the airplane designer's head into artificial intelligence that balances all these objectives. Someday, we'll continue to probably move to that end, but right now, the knowledge to design airplanes is in the designer's head.
Okay, you made the statement in 1990. Now, is it what is it talking about? 40 years ago, afterwards, do you still have the same issue, like where this knowledge, people still having this problem of translating the knowledge from the designer's head onto some CAD program? Something is happening, but not. So what we do is that once you do finish the knowledge-based design, once you're doing that, you kind of put it in something called a design repository. And then what happens is that once you do a traditional knowledge, conceptual design, for example, in this building, you say, well, I'm kind of deciding on this particular room like this, and this room is connected to the next room, and there's a corridor there. So these are all like symbolic kind of structures you create. But that has to be translated into some kind of a CAD program. And that's what the traditional CAD systems used to do, like ProEngineer. For some of you might be using this traditional AutoCAD, ProEngineer, and those kinds of things. They were mapping into that thing. So once you finish that, then you have this thing of doing analysis, like finite element analysis, simulation. So you want to analyze how the structure actually behaves. From there, the next step is this virtual prototyping environment. Now what you do is that you take the thing in the CAD program and give it some behavior to it, so that when I drop this thing virtually in the computer, it behaves exactly as it is physically. So there's a physics models incorporated along with this CAD program. See the evolution. Again, this is 1996 though, not now. So the next step then is the immersive CAD. At that time, I thought for some reason the virtual systems are going to take over. So you have this thing, the silicon human interface. So there is a actual silicon carbon interface around here. So now the human being is part of the system. So as you're doing design across the world, the virtual, you get into this immersive environments, but it so happened that it took off in the games. Actually, there's a history story behind that, because it took off in the games, and that's what happened to NVIDIA anyway, because of the games. We'll come to that later on. So there are other kinds of networks that that you have in this thing. So there are a number of things around here which I don't want to go into too much details, but the idea is that you have the standards, because all these things have to interoperate, and there's this infrastructure you talked about, and there's some organization issues. Now that's only one network. So then you have all the other networks which I talked about, like the production network and so on. So if you look at the future of manufacturing, there are several things that are happening. One is the advances in manufacturing technologies, which you can see that where you have innovative processes, robotics, additive manufacturing, sensors, and materials. Materials is a big thing right now, as you know, that critical materials, people are talking about this, a lot of investments going into the creation of new materials. Then you have these advances in manufacturing practice like management, supply chain optimization, predictive maintenance system. Then you have the advances in computing and information technology, and that's what I'm interested in, kind of thing, because a lot of people in the mechanical engineering world, they do these kinds of things. And there's this whole thing in the management world, they do these kinds of things. Then you have the advances in the computer systems and computer information technology or information computer technology, whatever you call it. Then you see there's a lot of stuff going on in software like PLM, AI, virtual reality, digital twins. So those are the kinds of things which are progress is being made. And then speed and storage, network communications and security. And finally, these things called MPCDs. MPCDs are actually mobile personal computing devices. I started calling this MPCD about 15 years ago, and I stick to that term. And the reason why I stick to this term is because actually I don't talk too much on the phone, except when I called you today from the parking lot because I couldn't get parking. But most of the time, either you're texting or emailing or doing something nice things along with this device. And this device actually takes over a lot in both in the healthcare and the manufacturing world, where people are using this quite a lot. I mean, you have this machine, you kind of take an image of the machine and do all kinds of things. So that's where we are right now, and this is the future manufacturing vision where you have agile, on-demand, smart, energy efficient, and stuff. So now I'm give a brief introduction to AI. Some of you, how many of you are experts in AI? Sorry if I'm repeating. And at least, okay, I know Tim. A couple of you at least. Actually, a lot of you, probably most of you are, but anyway, being very humble. So this is actually, the whole thing comes down to this notion of intelligence, okay? What is intelligence? So people have several kinds of definitions about intelligence, that this is a goal-oriented thing, which Ramesh came up some time ago. And the idea is to kind of understand what's happening around you and make some decisions based on that to achieve certain goals. That's one definition of intelligence. There's a whole problem with this whole definition of intelligence anyway, okay? Let's use this one, looks like it's easier. So any intelligent agent we talk about have these things, mental attitudes, it is perceiving and it can model the external worlds, it can understand, solve problems, generalize, plan, predict, and all kinds of things, okay? So now the question is that there are actually multiple types of intelligences, not a single intelligence. And we kind of measure people who get into, at one time, in fact, when you got into MIT, for example, since I taught there, you know this, they only used to look at one kind of intelligence there, how good you are at solving problems. Okay? Only of late, they decided that they wanted to have people well-rounded. Although one of the professors in one of the meetings claimed that well-rounded people are pointless. So he claimed, why do you want all these people who know about music and all kinds of things into the undergraduate program? This is for undergraduate program, not for graduate things. So that was the focus at that time, only intelligence in one dimension. But intelligence is multiple dimensions. So you got to understand that, okay? So now here is a very simplistic view of AI. The simplistic view of AI is that you have the environment, you have some kind of a perception. That's really our sensors here, the eyes, nose, ear, throat, and things like that. You're getting all the information here. And then the intelligent agent, based on all the information that it's getting, is making some decisions. Okay? Now the decisions in the output could be actions, which is either a language-based thing or some kind of a manipulator or like a robotics thing. We'll come to that later on. And also the terminology keeps changing all the time. And we'll also come to that later on, what these terminology problems are. So now I'll do a brief discussion of the evolution of AI. Actually, AI started a long time ago, not only now, because I call it as a prehistory, whereas the Paleolithic thing, where the Indian and Greek philosophers are talking about this notion of how do you represent the state of the being. They call it ontology later on. That's where the term ontology landed up. And Indian philosophers around 1000 BC or something like that came up with this neat idea of how do you represent knowledge in terms of what we call it knowledge nets and knowledge graphs right now. And they also talked about inference, like the kind of inference Aristotle was taking. But Aristotle gets a lot of credit for it. Okay, but you understand that this has been before, even about 1000 years before, and people were thinking about it. Anyway, those are the ancient, I call it the Paleolithic, and then you have the Neolithic area where you have people like Hume, Russell, Turing. And Turing was the one who came up with this thing called Turing test. I guess all of you are familiar with the thing. And it's kind of interesting because there was a recent paper in the Nature which claimed that we have achieved this artificial general intelligence because the computer, if someone cannot distinguish whether the answer is coming from a computer or a human, then the system is really intelligent. Okay, so then you have this thing called, how many of you have heard of this AGI? Okay, so there's a lot of, I think the people are barking up the wrong tree. That's a different story. We shouldn't be concerned about those kinds of things because it's really augmented general intelligence is what we want. We want the computers to help us, not computers to replace it or whatever it is, because we don't even know what intelligence is in a way. As you have seen, that people have given definitions, and there's all this. That's philosophically, you have to think about it carefully, because a lot of things which a kid can do, a 2-year-old kid, the computer cannot do. Okay, it's been going on for some time. Even language actually is an interesting problem in there. So there were like things, the beginnings of what AI term was coined, and then there's early years and the rise of knowledge systems of 1957. I started 1957 because that's the year I was born, so it's a good time to start that. Till about 1980, where you have things like GPS, Dendrel, hearsay, or speech recognition. Understanding is different. Speech recognition, SCMU, MySyn, and this is a big step into the knowledge systems area. So then finally we had this thing called in the 1980s to 1990, where knowledge is power. You remember Feigenbaum, he wrote this book on this knowledge is power, and everyone thought knowledge-based systems are going to take over the thing. You're going to make billions of dollars out of it and so on. Didn't really happen, but actually did something very useful in terms of the awareness that in knowledge lies the power. And then there was a lot of silent period, which is from 1990 to 2000, where you had seen this Deep Blue, the chess program, rise of the robots, commercialization of AI technologies. Although we didn't really, these are all happening behind the scenes. A lot of stuff was going on in speech recognition, natural language problem, understanding, and so on. But it was not so much hype created at that time. And in fact, I don't know how many of you heard of this naturally speaking dragon for speech recognition. In fact, most of the speech recognition programs, not all of them, many of them came from Roger Reddy's lab at Carnegie Mellon University. And this naturally speaking dragon, Jim Baker and his wife started this company, and that's became Nuance right now. And unfortunately, those original developers or the inventors of this didn't make much money, but someone else made the money, like everywhere else. So then we have this thing called the neural networks, which came in 2000 to 2015, which I call the second wave revolution, and mostly to do with deep learning. And what happened is that, in fact, Jeffrey Winton was at Carnegie Mellon University when I was there. At that time, neural networks were not given that much importance because in knowledge lies the power. Then something happened, around 2000s or so. Most of the, if you look at for this, anyone take courses in neural networks, you'll see a lot of it is matrix manipulation out there, because W0 times Xi, Wi times Xi or multiplying. So a lot of matrix multiplication is going on. It so happens that if you look at this video games or computer graphics, there's a lot of matrix multiplication going on there too. So NVIDIA was actually developing its chips for video games, those kinds of activities, but they were taking this matrix multiplication and it was hard coding to the system. However, at the time, same thing, neural networks was evolving, like Jeffrey Hinton and other people who are developing these neural networks, but computationally it was not feasible to do it on regular computers, but they can do it on this NVIDIA type of computers. So as a result of that, two things happened. NVIDIA stock went up, the neural network stock went up at the same time, because the sheer coincidence, luck happening. Otherwise, neural networks would have been there before, because large matrix multiplications are not very easy for the computation at that time. Although you have GPUs and those kinds of things coming up right now. So anyway, that's what happened. Then what people have realized now that these neural networks have a lot of limitations. So what we have is the symbiosis of the neural and knowledge networks happening. This is called neurosymbolic computing. We'll come to this briefly. So, and finally, there's something called the conscious machine. Now, it gives you a lot of people go back and think about it. Can computers be sentient? Can computers be conscious of the fact what's happening? How many of you think that computers can become conscious? You can make this. Yep, you think so? Okay, why?
I think it's been proven. Google had a situation a few months ago where they tried to shut down the computer, and the computer came up with all kinds of stories and blackmail and so forth to stay up.
So that actually is interesting, because I call it seemingly consciousness, actually, because consciousness no one understands. because there is the Eastern world of it and the Western thing. In the Eastern philosophy, if you go back, consciousness is defined completely differently than what the Westerners think about. But that's why I said seemingly conscious.
But I heard that when they allowed robots to connect to each other, they developed some communication, so-called language that the humans could not understand. They might figure out a very fast way of communication, right?
No, it's not the communication part of it. It's the consciousness I'm talking about. Okay, that is your sentient. You kind of you are aware of the world around you, and you make certain because of your awareness. You also make certain, the human emotion, human thought, and all those things come into picture. So these things are different from communication. Communication is part of this process, but it's not wrong.
The answer to that question is the same as the answer to am I conscious?
Am I conscious is the problem with am I conscious is a different thing, depending on the philosophy thing. Anyway, that's something to think about for the future for those of you who are just starting a life. So there's this, I briefly kind of go through this thing because in the time issues, as I call the first wave is the knowledge-based wave. I don't know how many of you have seen this slide around here. Has anyone seen this thing? So they do teach this in school nowadays, knowledge-based systems. Okay, you do teach. Okay, a lot of schools don't even teach this thing because there you have the short-term memory, the knowledge-based encoded into rules, ontologies, and logic, and they have several inference strategies here. And all these inference strategies, I actually wrote a book which came out in 1997, where I described each one of these inference strategies in details on something called intelligent systems for engineering at the time. So if you look at a typical design process, the evolution of the design, you'll see something interesting. Like as you go from the very, very low English type of statements to actually the solid models, you'll see there's a lot of representational schemes here. Like, for example, so sometimes it's pictorial, sometimes it's linguistic, sometimes it's virtual, sometimes it's algorithmic, and sometimes it's symbolic. So all kinds, so knowledge, so if you look at knowledge representation, you have to encode all these things in your representational scheme. It's not just your geometry. There's more to CAD than simple geometry. It's beyond CAD. And also things at the time went from at one time they thought the Earth was the center of the universe, okay? That's a Ptolemaic view before. And then it changed into Copernicus who said, no, it's the sun in the front of the center. So similarly here, from a geometric view, we are now going into what is a view of a semantic product view. So semantics is an important thing around here, and geometry is only part of it. So around in 1990s, at NIST, we developed this representational scheme called the core product model, where we include, where geometry is only a part of this whole thing, where you can see geometry, material, form come to the bottom. But there are other kinds of things like behavior, specifications, and all kinds of other things incorporated in there. So this representation was used by Boeing and a whole lot of people in their product lifecycle management systems. They took variations of this, and we don't know exactly what they did because I know that they have used it, but I don't know exactly where they've incorporated because many of the European companies use this, but they don't tell us exactly, proprietary reasons, I guess. And then we extended this thing to assembly, to do assembly also, where we have this artifact, and then we have this, because if you look at very carefully, many of this, if you take your car is actually assemblage of so many things incorporated in there. And tolerance becomes a very important part of this whole process. So how do you represent this tolerance, all of this? Again, this was, there's a paper here, which, and I give references to many, if anyone is interested, they can go into this thing. Okay, so around 20 years ago or so, again, I kind of talked about this open knowledge, the knowledge networks, because at that time I was pushing for a standard for knowledge networks. So the idea is that if you have an open standard for generating these knowledge networks, then what you can do is that everyone can develop a knowledge network in their domain, and you can combine all the knowledge networks to make a huge knowledge network. And as an example, you know how the Oxford Dictionary was created? Actually, it was created by people all around the globe sending in their contributions. In fact, there's a famous book by Simon Winchester or something like The Madman and something. Okay, you should read that book, where there was one guy who was like a little bit crazy. He actually contributed to, I'm sorry about this, I should have, this is Anupam, but I'll just tell you. Anupam, I'm at UMBC. So I'm sorry. An intelligent system could have answered. Anyway, so this So this is a very important thing, and I think I still believe in that the knowledge networks are extremely important. They should. So let's say, for example, you created a representation for like the core product model, which I talked about. Now I give it to UMBC Mechanical Engineering Department of Computer Science. Similarly, I give it to some people in India, some people in China, all over the people, they use the same representation. Now people in UMBC kind of develop a representation for the gearboxes, and people somewhere else can create a representation for your differential for a car. And people somewhere can represent it, can do it. Because the system can also do both electromechanical devices. Not only, I only show you mechanical part of it, but we develop representations where you can encode electronics and software also into this process as such. So imagine that. Imagine now, if you have billions and billions of people all over the world contributing, each one only contributing a very small thing, just a small thing. And then you combine all this knowledge together, what do you have? Just think about it. Okay? So anyway, so then the kind of all this open knowledge network is related to this notion of this ontologies, which I described about it. I'm not going to go into details about what is an ontology and so on. I think some of you may be working in ontologies, but it's just a mechanism where you have these entities, and entities are related to other entities, and there are mechanisms of inheritance and those kinds of things, which you can propagate your information across. So there's a whole spectrum of ontologies that are being developed, something to do with weak semantics and something to do with strong semantics like first order logic, depending on a lot of times what happens is when you want to exchange information, like I'm talking syntax with an accent, but that's a different story. Okay? So then this particular syntax, she has to mean something. That's the meaning part of it, that's semantics. So you need both syntax and semantics incorporated in there when you're exchanging information. And ontologies provide a mechanism of transferring the semantics. Even for a simple cat-to-cat things, what happens is if you develop in one cat some lines like this, okay, square for example, and if you send this to another cat system, actually it will be something like that because the precision is of these two cat systems are different. So as a result of that, it creates something else like this. On the other hand, if you know the semantics that it's a square, this one will create a square on the other one. So in every domain, I can talk about how semantics in healthcare and manufacturing, all of them, semantics becomes very important. But people kind of think that if semantics can automatically created by neural networks, but that's not really true because you need enough data to. So you have this this particular spectrum there. And then what we did was that we looked at it and said, well, there's some problem here. The problem is that if you look at that, that only is very good at predicate logic and those kinds of things. It represents logic. But if engineers require a lot more than logic, like Newtonian mechanics is part of it. So how do you combine Newtonian mechanics along with the predicate logic of the computer science world? So we came up with this thing called, actually we didn't come up, but we took this thing called category theory, which I started a long time ago. 1960s was actually developed in the United States, but the French made it popular. This particular thing is a mechanism, is a very formal mechanism which can represent anything in the spectrum. So again, if you're interested in category theory, I can send you pointers to that. There are a lot of papers we have written on that thing. So this whole thing of ontology, so there's a summit which goes on for, I think this is very important if you're interested in these ontologies to go to this. And this year's summit, we started the summit 20 years ago. And this year's summit is a culmination of what has happened over the last 20 years. Again, you can go in and have a look at that. So the second wave is the neural network wave. And the people thought at one point that we need to simulate the human being, or human brain. So if you look at the brain, there's a lot of neurons here, and neurons are communicating to each other. And they try to replicate that particular process. And you can see these neural networks where you have these things as neurons, and there's some weights, and these weights are constantly changed across this. And this one talks about a multi-layer model where there's an input layer and output layer. This to do with diabetic retinopathy, where it gives an output of one of these things, and this particular thing recognizes any of these conditions as such. Actually, interestingly though, when I published this book in 1997, which I actually written much earlier when I was at MIT, my book was about knowledge-based systems, and a chapter on neural networks in there. And people asked me, why do you have a chapter on neural networks in a book on knowledge-based systems? So I said, I don't know. Something is going to happen to this in the future. That's why I put it into the thing. By the way, this was in 1994 actually, I wrote this book. But then I also, in the book, I explained that really these two things have to combine together. Otherwise, things are going to go. So now we have these things called convolution networks. All kinds of networks have come into picture. Now, this was about 2019. I don't know whether you read this paper, the famous thing by David Gunning in the AI magazine, which came, where you said the problem is that what happens in neural networks really is that there's a function that is learned here. So this is the learned function. So then you show all these photographs or whatever it is and show it's a dog or a cat, and it learns some kind of a function with some probability, but it didn't do a lot of those things. It couldn't explain itself. It couldn't do any of those things, but it could tell you it's a dog or a cat. So then what you said at the time is that now you need to kind of have, solve this problem of explanation, understand why not, and things like that. You wrote this thing about the 2019 and DARPA had a program. How many of you think the neural networks can do these things right now? It's interesting. Think about it. Can they explain their reasoning process? Can you trust them? And those things, okay? So there's several extensions were made to these neural networks, like variational autoencoders, generative adversarial network, large language models, diffusion models, and you have this thing called physics-informed neural networks. Have you heard of all these things? Have you done work in this area? One or two of these things probably, okay? So anyway, in terms of I don't want to go too much into this thing, but the GNANs are very popular at one time, where you have a system generating, and which is called a generator, and that learns how to generate samples, and then there's a discriminator, which kind of discriminates between the real data and kind of the generated data, and you kind of train this process, and there's a very nice. Again, I kept these references around here, so if you want to learn more about it, there's a YouTube video on how this actually works from MIT. How many have seen these MIT videos? They're pretty nice, actually. So there's some generated images around here. Like, for example, one of the problems we had, we do a lot of stuff in image processing, and we couldn't get enough data for images. So what do? We use this GANs to generate images, okay? So we take some samples, and then we actually generate the images using GANs, and then we feed it back into the neural network. And there's a lot of those things are going on right now. They generate the data and then feed it into the neural network. Okay, but here you can kind of figure out which is a fake one and which is, and this kind of looks, the things are very sophisticated, and people, and you probably are familiar with some of the things happening, the fake videos and the fake images in the network, which looks like real. So whenever someone forwards me a video, I don't know if it's fake or not, it looks like, but there are some subtle things which you can look at it and see whether it could be a fake or not. So nowadays, whenever someone forwards a video to me, I make an assumption it's a fake video. And then I look at it. There's a lot of people have written papers in these things, and Andrew Kusiak has written a long time ago on, I think it came, I don't know, whatever year is that, 2020, about how these things can be used in manufacturing. Then you have these things called large language models, which have come out in the recent past, and everyone probably heard of this thing called Attention is All You Need by Vaswani. How many of you actually read that paper? And how many of you really understood what's going on in the paper? Maybe some of you. Okay.
Badly written paper.
Mm-hmm. But that I agree with you totally. Okay. It took me quite some time to figure out what's there. Actually, I kind of figured it out from these videos around here. Okay. So these videos here actually tell you in very nice detail, especially this one by 3 Blue and Brown, goes into very nice details of how this thing works. So you learn it. You learn that you'll understand much better than the original paper. So they did it anyway. And actually, they wanted to do it for language translations, really, the natural language translations. That's their original goal. And this was, by the way, in 2017. Now, it's kind of interesting. So people have become experts. After 2017, if you have followed this area, they followed this path, you don't really need to know what happened in the before. So in the recent past, all of these things happened in the last 5-6 years. So anyway, in terms of this LLMs, people work in LLMs here. If you're not working in LLMs, something is wrong right now. So these large language models, actually, it's kind of interesting right now. AI is becoming part of people's day-to-day activities. You ask anyone nowadays, even the person walking on the street, what do they use? They use generative AI. They go into Google and it has a generative AI. So almost everyone is using. So if everyone is using this thing, that's what people will believe is the truth, because that's what they're using all the time. Okay? And I remember in about 3 years ago, I gave a talk on AI in medicine to about 40 or 50 physicians, and they never heard anything of this thing. And I showed how ChatGPT actually can do pass the USMLE exam, except it failed the IIT entrance. That's a good story. So how the ChatGPT, now it's smart, maybe it could, how it works, what are the things. And no one had any clue about what it is. Now, if I meet the same doctor on the street, he says, yeah, I'm using it every day in my practice. Then the question is always asked, will these LLMs and AI will replace doctors? And my answer to that is that, yeah, it will replace those doctors who don't use AI, but it's not going to replace doctors. So similarly, same thing is going to happen to engineers as such, okay? So these things are going to take over a lot, but there are a lot of problems with that, as you all know. Okay? So anyway, you know this, what ChatGPT is. It's a generative pre-trained transformer, and it's supposed to generate text. So there is a Gemini. Have you heard any people use this from Google? Gemini. It's a pretty neat system. And there are a lot of neat systems. Actually, I don't know how many of you use this Grok AI. It's pretty neat too. You ask about yourself, it knows more about you than you do, okay? So these are the kinds of things that we can see. So you can ask us, what is Tim fine and famous for? And it gives you so much, and Tim will say, have I done all these things in my life? It's pretty good, okay? Try it. And here, like for example, you can say, what does a fuel injection service do? You can ask a question because you're on the manufacturing floor, or for in a manufacturing world, you want to know about this fuel injection. And actually what it does, I think, this is a controversial thing which we don't know exactly, but I think this is my personal view, it just kind of takes this, it's parsing this sentence, fuel injection, okay? And then the fuel injection service, what it does is next is feeds that into an LLM, and the LLM kind of trying to determine what is the next probability using this transformer architecture, what is the probability of the next sentence, okay? And the next sentence could be, cleans could be the service picks up. And that's again fed back into the transformer. And then it's a process that goes on and on and on. And it's kind of expensive, but then they've done all kinds of neat tricks. So you kind of get this output from Gemini. This is what it does actually. So this is how Gemini used to work, but now they have other things. So, but then I think nowadays they're using these knowledge networks, because once I asked a question to Gemini, do you use these knowledge networks? And it said yes. Okay. So it's a fake thing or not, or the things are not, but they're using some kind of knowledge networks. It's not like purely neural network based thing.
But it would be also too much time consuming and energy consuming to reinvent the whole knowledge yourself, right? I mean, if the knowledge is already there, might as well use it, right?
Yeah. So that's what the knowledge networks, people are creating a lot of these things, especially in the private industry, because it's their bread and butter kind of thing. They won't tell you that, but they're doing it. Then what we are now coming into this thing called agent frameworks, and we have this agentic frameworks, and there's a new buzzword on agentic frameworks. But then if you go back about 40 years ago, Tim can tell you about this thing, is about agents were different at that time. Initially, there was this thing called the Blackboard framework, where you had this Blackboard in terms of this inference mechanism, all of this knowledge sources they call it, but they're really like agents talking to one another through a Blackboard, and there's a master agent. Then again, it's I kind of talk about this in my book. If you want more details, you can look at that. And then at CME also around the same time, with something called A-Teams approach came in, where you have several kinds of agents going through a solutions page, and each of the agents don't know anything about each other. The construction agents, improvement agents, evaluation agents, destruction agents, and then some other create the solution into the system. Okay, it's a very neat system, and it could solve this very interesting problems. One problem it could solve is a porcupine problem in terms of optimization, because if you look at the space, which is like a porcupine, it's very hard to get the actual optimal such, and this could solve very easily. So there's the good olden days of agentic AI, and again, it's there in my book if people are interested in knowing it. Now we have what is known as agentic AI with these large language models. And what people do is that they have these LLMs, they have these clients, and there's model context protocols, and they're communicating through it, through getting, where they can communicate with tools, with other agents, with clients, and so on. So that's what is happening right now, agentic AI, if you have heard that term. That's what it is. Okay, now the next step is, actually this is happening in parallel, is this thing called physics-informed neural networks. You have the neural networks, and then for those of you who kind of are actually working in neural networks, or you've been taught a course in neural networks, you'll see there's something called the loss function around here. So you propagate, you go in this direction, find out what is the difference between the real situation and what it predicts, and then you get an error and you feed back into the thing. So what you do in this physics-informed neural networks, you add physics to the problem around here. So you add the output to it, and your loss function now is a combination of the loss function in the neural network and the loss function around here where you solve this equation. So you combine those two things and feed it back. So there's a nice article here, physics-informed neural net. I'm not going to do details in all these things in the interest of time, but I'll give you pointers to that. So here is this guy named Steve Button has a very nice video. He explains how this works. Like here is an example. Like if you try to train the system with this for this harmonic motion, and you see that most of the time in engineering, where it's mx double dot plus some cx dot plus kx equals some forcing function, and you want to know what's the output of that, you will see some kind of a result like this. But without the physics-informed things, the neural network, what happens is it kind of goes all around the place. Whereas if you put this physics-informed neural information in there, it actually gets to the right answer. Like this, very fast. It converges very fast rather than forever. So that's something which is also happening in there. So now we have what is known as a neurosymbolic computing, okay? Because the neural networks, you can train this neural network to this image recognition as guitar or a penguin. But then what you can do is that you can fool the thing, change a little bit in the input data, and you think this is a guitar and this is a penguin. And people have shown all kinds of things like just changing in the background a little bit, adding some noise. I think this gibbon and not a panda. So those are the things that are happening. And the worst thing that is disastrous thing that could happen potentially, okay, because the neural network, what it has done is it has learned a function. Now you can do several things with it in terms of adding trojans. Either you can manipulate the input data like we have seen in the panda case. You can manipulate the learned function. So you can go in and change the weights or do something in there for open source models. And you can change the output too. You can put a trojan in the output. Here's an example. Like for example, if you train this Tesla machine for a stop sign, and then you put a post-it note, it thinks it's a speed limit kind of thing, 35 miles per hour, and it goes through. So you can manipulate these systems at the input, the learned function, and the output. So you can add trojans in any of those things. So that's an interesting field. Okay. So anyway, I'm going to, there's some nice books in there if you want to go through it. Rebooting AI, Gary Marcus, in this AI Snake Oil, again, interesting book. There's a conversation between this guy, Gary Marcus, and Joshua Benigo, and there's a link to that. We should probably go through that thing. And anyway, I'm going to, then you can go through the book written. So anyway, there is the reason is that neural networks are good at doing certain things, and symbolic networks are good at doing things. So I'm going to skip these things except show that there's something called Dan Kahneman. This thing is a photo out there. He wrote this book, Thinking Fast, Thinking Slow, or something like that. So you can see these things can be categorized into system 1 and system 2. So system 1 is your neural network 1, and system 2 is this knowledge graphs that I talked about. So you have to combine both the system 1 and system 2 to make, then you have a very nice system that's going on. So again, I don't want to go into details of these things. So now I'm going to go through some examples in manufacturing quickly, maybe in the next 10, 15, 20 minutes or so. Actually, this talk is about manufacturing, but I thought I'll just give an overview of AI. Now, I don't know how much I've repeated, but I tried to kind of condense everything into these 3 waves and then finally show you why the neurosymbolic computing is important from a computational perspective. Now I'm going to some examples of manufacturing. So if you look at the whole engineering part of it, there's what is known as the derivation formation spectrum. And I think the spectrum was first taught by Kulikowski or someone like that at Rutgers, you know. So they wrote this thing about the, no, it's not Kulikowski, it's a gentleman who was at Rutgers. You remember the Rutgers? Sam, Amaral, you know, Saul Amaral? He wrote this thing called the derivation formation spectrum. And the idea is that at this end of the spectrum, in any problem solving, you have things like diagnosis, classification, control. And these are called derivation type problems because they're classification things. Like if you want to know, if you have a car and the car kind of malfunctions, you want to know what is the problem with that car. So that means like the car stops, problem could be in the carburetor, car problem could be in the fuel injection system and so on. So you can derive where is the problem in their case. So these are simpler problems, okay, derivation problems. And the world knowledge-based systems used to be very good at it in the 1980s. But there's the formation type problems where you have a set of constraints and you have to design. Like car, there you give a set of constraints and you design the car. So that's the design problem. It's a formation type of problem. It's a generation problem. So this is the list of problems that you see, and most of my research in 1980s was on design. So in terms of the diagnosis, again, I don't want to go into too much detail about it. In 1982 to 84, we developed this thing. Like, have you been in Atlanta? Anyone in the People Mover? So at that time, what happened in the People Mover is that the doors used to open and the doors used to close automatically when the thing is going. So it's dangerous. So they came to Carnegie Mellon University and said, Westinghouse at the time, they were the ones who built that system. Can you build a diagnostic system so that it will tell us, what is a potential problem as such? And it so happened they gave it to the civil engineering people thinking it's a transportation problem, but it's not a transportation problem. As such, it's more of a device diagnosis problem. So we kind of came up with at that time, there was something called, again, historically, there was something called Prospector. Some of you might have heard of it. And they developed a domain-independent system called CAS, Knowledge Acquisition System. And we used that. It was initially developed for geology, and we took the geology knowledge out. It's a domain-independent system, and we used it for this particular thing. Again, it basically it has a number of subsystems, and you have to come up with the appropriate problem diagnosis where it happens. It's in this particular cabinet. We had to learn a lot of electronics around here, and also a lot of interactions with these experts. Initially, they didn't want to give us any knowledge, and finally, we have to tell them we are poor graduate students trying to survive. So then it's okay, whatever. We are trying to build this system. There's a long story about this, like some other time lunch meeting. But anyway, this system kind of used this inference networks here, where you make a diagnosis and you make the corrective actions in there. And again, this is all symbolic in nature. So then that is for the diagnosis part of it. Again, in the interest of time, I didn't go into details of it, but then you have to create this inference network and you have to go through this inference network. And the advantage of this system is it could explain why it make a particular decision and so on. Except that the Westinghouse people wanted it to scale it. They said, if you give us $1 million, can you scale this up in the next few months? And that was not really feasible as such. At that time, you're talking about, we are working on a VAX computer. For those of you who know what a VAX computer, going remotely. We went to Atlanta to demonstrate the system. It used to take forever to give a particular answer. By the time the train would have gone somewhere else. Okay, so these are the kinds of problems we faced in 1982. These things have been used for interpretation, where based on the data, we interpret in this case whether the system is going to have the nuclear things. Then you have these things like weld detect classification, and here again the system. The welding designer kind of takes a photograph with a smartphone, and the system kind of determines what is the problem with this weld. So here is a framework which Saundar Kumar developed at Penn State. If you want more details, you can Google this guy. But in terms of our work, we have done this. What we have done is that we took these 4 samples from a number of nuclear reactors, and then using neural network-based image processing, we can kind of determine that system has learned a function so that it can determine whether it's a good about the in terms of the defect. I'm just simplifying this thing, whether this defect is going to cause some kind of a failure or not. Okay, so then if you take a new nuclear reactor and if you have some other reactor and take a small sample from that and feed it to the system, and it will tell you based on its learned function before. Again, it's interpreting the data which is coming from these images. This is interpretation. Then you have this notion of prediction or predictive maintenance. And on the shop floor, you have a lot of these machines, and these machines are giving out all these signals. And based on the signals, you want to know how the machine is going to, what the machine is going to do in the future. For example, you can go from basically from the component level onto the system level and on here. Again, this is due to Saundar Kumar who was doing work on this particular area. So it's very interesting problems. All kinds of problems occur here in the predictive maintenance. Okay? And like there's all these machines which are going on, and they're taking the signals, and based on from the signals, you kind of find out what is potentially going to happen. And then you can even go back to the machine and correct it automatically. So there's this whole field on predictive maintenance, which I think a lot of funding is going on at this stage in the manufacturing floor. Again, if you're talking about the manufacturing supply chains, now supply chains are a very important part of this whole process. And the reason is that if you go back to the COVID times, they were trying to manufacture these ventilators or whatever it is, and there's a big problem in the supply chain. Similarly, in these chips, there's a big problem in the supply chains. there are a number of problems in the supply chains, which I can talk forever, like, for example, optimization of the supply chains. In this case, prediction of times. When is your goods, when are my goods going to come here? Because the goods are going through several places, like they manufacture in China or something like that, or they can come to the United States. And several things are happening across this journey, and you want to predict what time it's going to. So there's a prediction problem. So then you have these problems of monitoring, and you have the design problem, which I worked on. So again, the design, you give a set of specifications, and you want to build the things. Like in this case, you want to build this a power plant kind of thing. And if you take the turbine engine around here, people have used here both neural networks and knowledge-based design to do this, to solve this problem of designing the turbine in the power plant. Here's a power plant, turbine. They use these kinds of techniques to design that. Then Hamad at MIT uses basically uses not large language models, but the diffusion models and variational encoders and those kinds of things to generate bytes, various kinds of bytes. And he came up with some innovative type of bytes. So if you're interested, go to his website here and check out his current things. You can do some simulations and so on. And the other thing which is happening in the latest trend is Marcus Boiler at MIT has done some very innovative and important work in materials design. Okay, so what the system does is automatically generates this new materials, and not only that, it is connected to the manufacturing processes. What kind of manufacturing processes you need to use for the materials that you have generated. Again, you can go to this website, Marcus Boiler's work, and you can see. And this uses both neural networks and the category theory, which is the one. Remember, I mentioned category theory before. So it uses some kind of a neurosymbolic computing to do it. And the next step in this area for some of you who are doing PhD theses is scientific discovery. Can I discover? Remember in last year, they got a Nobel Prize for what? Protein prediction? Or protein folding, sorry. The folding, if you're given a sequence of amino acids, how does this protein fold? Only folding they came up with, but they didn't come up with the mechanism of how this happens. Only the final state of how the protein will be, not how it goes from amino acid sequence to this particular protein. So in the future, and again, this is a challenge, when will the computer automatically come up with the whole mechanism of how this protein folds? And that's a Nobel Prize. Anyone planning on that? Okay. Anyway, there are a lot of these commercial applications going on, and it's talking about supply chains. Now, the last part of it is I'm going to talk about 5 to 10 minutes on this area, which is becoming very popular right now. It's called the physical AI now. Now you've seen the symbolic AI, you've seen the neural networks, and then there is, if you go and Google physical AI, you'll see this now. And the physical AI is what NVIDIA, IBM, all of them are putting tons of money into this physical AI. So they go to this IBM thing and they'll tell you what physical AI. Actually, it's basically robotics, in my opinion. That's a different story. They call it physical AI. It's good to know the buzzwords. So this is a thing with SK Gupta at USC is working on. And what he does is this surface finishing of these things, and this kind of robots learn. And the robots now has to go through several stages. And let me see. Another example. I think I should. Yeah, it goes through this process where what happens is the human being actually teaches the system of how you do the finishing. And this robot actually learns from that how the human being shows. Okay, I think, let me see if I have an example. Yeah, here is an example. Okay, so the human being is kind of teaching it how to do the surface finish over there. And once the human being kind of teaches it how to do the surface finishing, the robot kind of learns this process. And not only the robot learns about this process, but using reinforcement technique, it actually improves on this process. And the robot not only improves on this process, now we have multiple knowledge sources that it has to create. Not only this, because there's a whole of this world models of this knowledge. And it actually creates, those things are automatically creates on the thing, and then it kind of does an efficient, whatever it is, it learns for many mistakes and things like that, it improves on its knowledge, and multiple skills have to be improved too. So this is some of the work that is doing. So I'm going to kind of skip through these things and go through the, yeah. So anyway, you have to clearly understand what's the difference between AI and augmented intelligence. Like, for example, people think that the factory floor of the future is something like this. Everything is done, but that's not going to happen. Human has to be in the loop. That's why I call it augmented intelligence. Forget about this artificial general intelligence. Concentrate on augmented general intelligence. Can I augment the intelligence is what you have to focus on, not whether can I replace the human being completely, which is going to be a tough job, okay? And some of the work that we are doing at NIST, if you want to know, you can go to this website that I have provided here. We have something called the AI risk management. One of the talks I generally give is AI metrology. How do you measure AI systems? That's the AI metrology part of it. Then we have AI evaluations. We need to evaluate the systems. Then we work on standards. And also we kind of, belong to the executive, so Department of Commerce. And the president, the White House has released this thing called Winning the Race American Civil Action Plan. And I would suggest all of you to go through it. And they mention this a lot of times in that particular action plan around here. And then we also have this, launches this Centers of AI in Manufacturing, because NIST is interested in accelerating the use of AI in the industry. More than the actual fundamental research which is being done in the universities, we can work with them, but we want to accelerate and show in the next few years of how, what can be the impacts of AI in the industry. And it is working with MITRE, they're giving them a grant, $20 million grant or something like that as part of this. And you can see the website there. And they're going, I think the same announcement, they said that they're going to also give X amount of money for a future manufacturing actually center, okay, which is run by both the industry and the academia. Okay, so anyway, there are a lot of these things. I'm going to skip this manufacturing architecture. So that's from DOE. There's a smart manufacturing programs called SESMI. You Google SESMI, CESMI, and DOE has spent almost a few $100 million on this thing. So you can check it out and see what they have produced. And there's a lot of these things about smart manufacturing that there. And there's a report that came out a few years ago on resilient manufacturing. Resilient manufacturing is an interesting thing. What do you mean by resilience? Because what happens in this is all manufacturing networks, I've talked about, especially supply chains. What happens if that thing is the supply chain, there are problems based on, like COVID is a thing, some unknown circumstances, there are problems in the supply chain. How can you be resilient about it using AI techniques? Okay, so you kind of predict the thing using AI techniques, and then you can make some recommendations and so on. Okay. So anyway, there are a lot of reviews of AI in manufacturing, and I have given a list of these things. The most recent is this National Academy's report, which gives options for a national plan for smart manufacturing. So you can go through it. And there are a number of these papers here which talk about AI in manufacturing reviews. Okay, and I've actually started a journal called AI in Engineering in 1986, which got changed into something called Advanced Informatics or something like that. And then we did a 3-volume series on AI in design, and then there's my book on AI for engineers. Okay, so for those of you who know Jim Gray, he used to work on data sciences. I think you know Jim Gray, Microsoft. So he got lost in the sea. So they did a symposium on him, and it was called the fourth paradigm. It's basically data intensive computing around here. Then we have the fifth paradigm in terms of the knowledge revolution and the internet. Now we have the sixth paradigm, which is the rise of the neural networks, which happened, and neural networks are going to take over and so on. And finally, we have what are known, which I call the smart network systems and societies with neurosymbolic computing. That's the seventh paradigm. You might ask what's the eighth paradigm, but it's only 7 days in a week, so seventh paradigm. Now, only the first book is published. Rest of the things are my imagination. Yeah. Anyway, actually what happened is in the last 1 month, both of my mentors passed away. They were 90 years, and I owe a lot of my career to them. So that's why I'm dedicating this talk to them. Okay, I think I'm gone over by about 10 minutes, but I think I gave you I don't know, this super fast trains going, introducing AI from my perspective, and also how this is applied to the manufacturing, And remember the derivation formation spectrum, where you have problems at one end of the spectrum called the derivation type of problems or classification problems, and you have formation or the generative type of problems like design, planning, scheduling, all of them come at this end of the spectrum, whereas like diagnosis and those kinds of things come at this end of the spectrum. And also keep in mind that you really used to, it's a neurosymbolic computing is the one which will be the next, this decade's AI kind of activities that will go on. And all these things, there is one thing which you need to evaluate these AI systems. How do you evaluate these systems? That's a different talk completely. Okay, thank you.
Thank you very much. Well, we have time for some questions. Anybody have some? Please raise your hand and ask.
Okay, I can ask one. Nobody's asking. Okay. So, can you give me a non-trivial example of something that data analysis programs, software or whatever, right? Not humans. Analysis, let's say software or whatever, has figured out that we humans had completely missed some correlation somewhere, I mean.
Okay, so there are a number of examples in terms of protein prediction is a, the protein prediction is it's a hard problem for humans to even do it, okay? Okay, there are some problems which is, okay, like take for example, if I ask you how much is 17 times 17 for the kid doesn't really, very hard to do it. In a calculator, it takes no. And then I say 17 times 17 is 289. What is 17 times 17.345 times 17.456? Much harder, but the calculator does it in no time. So there's some tasks which the computers are really good at doing, and there's some tasks that human beings are good at doing. So that's why it has to be a human-computer interaction kind of thing. But the computers do a lot of those things which you don't even kind of realize that materials design is an interesting problem, like Mark Boyle's thing. It came up with some really neat new materials which we wouldn't have come up with. But at least we can use our intelligence to see whether it's something which is useful or not. And that's going to happen. Similarly, for cars, you can use the AI techniques to configure it initially, but then later on, it'll be a different story in terms of how good is this. And so you do a lot of these tests and things like that. So you can't let the system go wild and do whatever it wants to do. But there are some.
I have heard of just one, I mean, some sort of, I don't know whether it's real or not, but one example, right, where almost like a joke, right? They put together, they store the beer supplies and diapers close to each other. You heard of that?
That's data analytics. That's different. Because there they were looking at patterns.
Exactly.
Yeah. So again, there's another problem because these patterns kind of came to a conclusion. I think people who drink beer also like diapers or whatever.
No. I mean, the young dads, their wives send them to do the task. Right?
They're getting coupons.
Yeah.
They were getting coupons from Target. Okay? Yeah. So people who buy beers, are getting Target, something like that. I don't know whatever they're doing. They're buying things and they're getting these coupons for something else. So the system kind of figured out that you have a baby in the house. So those are the kinds of things that the systems can do automatically. And there's a lot of things which has happened over the years in data sciences. For example, people are talking about first generation, second generation, third generation. Like some of you might have heard about this CMMI for software development. Similarly, for data science, people came up with this CMMI kind of things. Whereas your refrigerator at the end is so smart that it will tell you that you're going to run out of milk tomorrow, and not only that, it will tell you Costco is selling this lactate milk for $5.49. But however, it will take you from your house to Costco is about 20 miles, so it will cost you about $2 to go and get it. So you're better off going to Walmart, which is next door, and buy it for $5.99. So those are the kinds of things which people have predicted a long time ago, and some of those things are happening. And you can see your mobile systems, the computer, the MPCDs that you're using. A lot of times it's telling you all these trends, what happens and things like that. But where it's going to make, in my opinion, the maximum impact right now is in healthcare. So we are going to see this whole evolution where we are going to have, it's going to be more of patient-centric than doctor-centric. So all your health records and everything will be on the system and based on the signals. And in fact, I was in Ford giving this talk, something like this about 7 or 8 years ago. And I told them, your car actually will be a healthcare system, okay? Because there are so many sensors. You're driving the car on the highway, and suddenly you find yourself in a hospital. Why? The car will take you to the hospital. Why? Because the car detected that you're going to have a cardiac failure. It detected that and it will take you there automatically. So that's my prediction 7 or 8 years ago, and maybe happening, I don't know, because there's so many sensors in the car detecting, constantly monitoring you. So the business model changes. The business model is not taking people from one place to another place, but making sure the person reaches safely and in a good health. So in other words, the manufacturing and the healthcare will be intertwined around here. So everything will be intertwined.
Yeah, I 100% agree with that.
Is NIST responsible for putting checks and balances for the development of AI in a lot of the industries?
Well, the answer is I cannot answer that question for so many reasons. So, but we are developing. Basically, we are developing frameworks so someone else actually does it. We are not a regulatory agency. So we only do tests and those kinds of things, recommendations. But we like the AI RMF is something which will help you to determine the risk of AI in a particular, manage risk. And there's a lot of stuff around here. You can go into the website and look into it, okay? So, but NIST is not a regulatory agency.
Thank you.
Yeah.
The large language models have captured an enormous amount of knowledge from all the written text that consumed. But sometimes I think that there's a lot of intelligence in other animals that don't have human language, or any kind of language like we do. So maybe physical AI addresses that. Do you have any thoughts on what else should be learned that can't be captured in language?
Okay. See, the problem is with the large language models. Originally, when they started, they were because they were only generating, and people said these models were something like hallucinating or something like that. Okay. Actually, that's not hallucinating. That's bullshitting. Okay. Because if you randomly generate something, I get bullshit. Hallucination means certain things. Like if you're a schizophrenic or something like that, then you're seeing you're imagining things which never happened. So that's kind of hallucinating. I don't know why they call this hallucinating. But what they've done is they've done a very smart thing in terms of using some kind of a knowledge networks so that it doesn't do it as much hallucinating as they used to do it. But still, human being has to take care of it. Now, your question you asked is a little bit interesting because it's much more than that. There's a model of a language that people have in their mind. It's a model. And animals also have some kind of a model, just that they're not able to speak to you, except that the dog may understand you, but you don't understand the dog. So the dog is looking at you and said, what the hell, is not understanding me. When he says sit, I sit. But when I'm asking him to go get me some food, he's not doing it, okay? So there's a different kind of intentions. There's a whole thing of intentions. But then actually, what is talking about natural language things and using large language models, there is a whole field of natural language processing that went on before that, and you should not neglect it, because those are the techniques that you can use with a combination of these LLMs to generate terminologies from this text. So they're very good for generating terminologies, but then you have to use a combination of these LLMs along with the linguistic theories which have been developed. Both of them have to be used, and we are working on that in one of the projects in terms of standards documents, where we can scan through them and develop the terminologies, find the circularities in there and so on. But we don't really use large language models for that, but we use the linguistic basis behind that. Some neural networks can be used, but most of our thing is based on a linguistic discourse. So people, for some reason, are neglecting that particular thing, but I think that's an important part of it.
So if you could render it into images, right? I mean, so a picture is worth 1,000 words, right? So I mean, a picture might convey the meaning of the paragraph better than anything else, right?
No. The picture, it generates when you generate the picture, the problem with generation of they're getting very sophisticated if you look at it, okay? Like you can go into the computer and say, generate a picture of Krishna and Arjuna riding for those of you who know about the Gita, which Oppenheimer mentions in the movie, okay? Of course, the context is very different when he mentioned that. So the system kind of gives you a very nice picture of Arjuna sitting in the back, but it takes several iterations it gives you something first, and then you say, I want 5 horses, it will put your 5 horses in there. So you try playing around with it. It does those kinds of things, okay? But again, as I said, these systems are becoming more and more sophisticated. And in fact, there are movies which are generated using the systems. Like they say, you write a script, actually the system kind of writes a script, and then you can generate the movie, and you can see all those kinds of things right now. So things are becoming sophisticated, but you got to be careful. But there's some fundamental research problems that you need to address in all these things. And from NIST, we are interested in the methodological, how do you measure these things is what we're interested in. Like if you have a large language model, how do you know this large language model in a particular context is giving me the right results? So we came up with a set of, in the medical world, we have a set of metrics. So similarly, you can come up with a set of metrics to see how well these large language models do. Even in agentic AI, for example, one of the fundamental problems is you can ask the system, for example, to create a bomb, okay? But then the system should have guardrails in saying that you cannot do that. Although the systems can do it, they should immediately come and say, stop it, you can't do it. So we need to develop those kinds of guardrails. And you've seen what happened to Grok in terms of what kinds of images and things it has been creating. Yeah.
Thank you for the call. So the question is, could you please talk a little bit more on the category theory?
Pardon?
Category theory part.
Yeah, category theory is actually, if you send me an email, I can send you the papers and the lectures associated with it, because it's based on a set theoretic kind of approach, but it's a very formal way of knowledge representation. So you can represent whatever you can represent in UML and those kinds of things in category theory, but it is a solid mathematical foundation. That's what it is. That's what makes it very elegant.
So from mathematics, it's about different mathematical structures and their relationship.
Yeah.
We're using that for manufacturing. How that.
There are some examples. I can send you some papers associated with that.
Yeah, thank you.
Question on the robotic AI, like today there are maybe two main types. One is like arms ship, right? Another type is like human ship robotic. Some company like Elon Musk figures or Boston Dynamics, they are doing the human ship robotic. And from the perspective of manufacturing, how do you think of them, and which one do you think is the future?
No, but it's called physical AI by the time right now. For some reason, the robotics is not our embodied AI, physical AI, they call all kinds of things. Now, these systems are going to be there, but I think in the manufacturing world, the human has to be in the loop. You can't let this system, they do some things which are good, but someone has to be guiding the thing. Otherwise, you can land into disasters. Because what happens is that a machine, for example, is a predictive maintenance. It goes and has the spindle speed is increased quite a lot, and the system goes and has this large language model. What's the potential problem based on the symptoms? And the system gives back an answer. And it so happens that the answer is not the right thing with that correct environment, because what are the large language models are doing? They're just picking up things which are there on the internet. So the human being has to kind of realize this is, you can use the guidance, but that's not the right thing. So they have to make the changes. So I believe that the human has to be in the loop. I mean, like, for example, the robo vacuums you have, they do that, the certain tasks are done very, very well. And, they're getting smarter and smarter. Those tasks, maybe that's okay. They can do it. But for certain tasks, you have to have the human in the loop. But may not be that much of human in the loop, but you have to have some control. Yeah.
You mentioned AI, manufacturing AI in healthcare. What areas in the future or in the near future, probably not in the next 5 years, that's probably going to be in like 20 years. How would AI in manufacturing affect like healthcare? And
no, there are two things in there. Okay, now if you look at the whole healthcare domain, again, as I said, it's a separate talk completely. In healthcare, there are two kinds of things. One is the soft, and another is the hard kind of thing. The hard healthcare are the machines, like you have devices, implantable devices. I mean, you have devices measuring your pulse rate, everything. So there's hardware here, and there's a software part of it also. Like, for example, you have electronic health records and genomics and those kinds of things. So there are two things which are happening simultaneously around here. So, and AI can be used in both at the device level and in the healthcare, in the EHRs, because the EHRs have a lot of information and the AI systems can do a prediction. There's something called P9 medicine we came up with. If you Google P9 medicine, you'll know how AI can help in all these things in the healthcare world. But the manufacturing world has got certain interesting problems. Like one of the things in manufacturing world we have is interoperability that we do, because all these machines have to interoperate with another. So we develop some techniques for interoperating. And the same thing in the healthcare world, we have the same problem. Like you have the EHRs and you're talking to another EHR, and there's an interoperability problem too. So you can take the knowledge gained in the manufacturing world in terms of interoperability, and you can apply that in the healthcare world. So you can transfer the knowledge. So what happens in the future is that I think transdisciplinary engineering is what it is. So what that means is that you take this, there are several kind of, you can use single discipline, I can work, heat transfer. Then I have multiple disciplines working in there. I have heat transfer, I have structures and so on in the airplane design. So there's a multidisciplinary kind of thing. Then you have cross-disciplinary kind of things. I learn in the biological world and I map it into the physical world, like Velcro, for example. And it was some plant which was interacting with other plants into sticking. So that was transferred to, knowledge was transferred to the biological, from biological to engineering world. And similarly, you have transdisciplinary, where you not only deal with all this cross-disciplinary, but you also have the social aspects of the thing. So now social aspects come into picture. So these are all socio-mechanical systems.
Okay, so like for example, those physics informed neural network, or also those physics AI, they are mainly domain specific. So their model is small. But like on the other hand, so for example, the LLM, they stick into the scaling law, right? So they build really large models. So how do you think about those gaps between them?
No, there is I'm sorry, I didn't quite get the question, but the LLMs are doing a particular purpose as such, but they're based on the neural networks kind of thing, okay? So the physics-informed things may not be using the LLM technology, but they're using neural networks and they're combining that with the physics of the problem.
Yeah, the thing is like,
you can combine them in some way, but not.
Yeah, the thing is like some of them, like for example, the physics-informed neural network, they are so domain specific, so they cannot solve more than
that particular
this
domain.
area. So, but like for the main chain for nowadays, they try to use the LLM to solve anything.
No, the LLMs are good for certain things. Okay, so you got to be careful in all these things. You got to understand what they're good for. Okay. So they're good for getting some answers, some configuration, something you can do with LLMs. But this particular physics-informed thing is very specific for solving some physics problem. Like, for example, you have computational fluid dynamics or something like that. These are very good at where you don't have enough data coming out of your machines. Then you can attach the physics onto that neural network. Again, it's a neural network-based kind of thing. LLMs are much more than neural net. LLMs are a kind of a neural networks. That's why, if you look at it, I classified them into autoencoders, generative thing, LLMs, physics informed. So these are all classifications, and you can use combinations of them if you want to. Depends.
So do you think like, is it possible that the physics informed can be extended more than one domain?
Potential.
Yeah.
There's potential.
Do you think there's any possibility?
No, I think it's a potential to do that, but I've not thought about it. But I'm sure it's a good PhD thesis. Yeah, I think two more. I think we're running out of time.
I like your opinion on the barriers for adoption of AI in society. For example, in the healthcare example that you gave, let's say that AI has a possibility of giving a correct diagnosis in 99% of the cases, but that 1% is going to result in a lawsuit. So some hospitals would not be want to take the risk. So that would be a barrier for adoption of AI. What do you think other barriers are in?
Well, actually, there's something called the AI risk management framework, which kind of whenever a company is going to establish the use of AI, they better go and look at the NIST AI risk management framework to see how to manage this risk. There's a whole different other problem about society and things like that. I don't want to go into that.
Yeah.
So that's a movie kind of. I think we have one last question. Someone in the back has been raising your hand.
Yeah. So I was wondering about the physical AI you are talking about. So do you think the bottleneck now is more about like AI won't come up with like good ideas or like the ability of the machine to implement them or something else?
The physical AI is actually robotics in a different, they are using a different terminology for that. But as you see in the example from USC, there are several layers. Like you teach the machine learns using reinforcement learning, the machine corrects itself, and then it develops a set of skills which are again used back into the machine. So that's the current state of the art. Okay.
Well, why don't we thank our speaker for this really interesting presentation.
Thank you.